Hello, I'm Stephen Bennett and I'm going to present a case study on the effectiveness of PALS based in Asotin Creek. Here's an outline. First I'm going to review the setting and the problem. Then we'll look at the potential solutions, followed by what we found both from the physical response side and the fish response. And then I'll just give an update on the status of this case study. Just a quick review. Remember how structure, large woody debris in particular, forces complexity through different pathways. First of all, the wood changes the hydraulics, which then leads to geomorphic processes, formation of bars, pools, and different planar features. And these are the habitats that fish require to fulfill their different life history needs. Just a review of the restoration principles that are maybe most appropriate for this particular case study. These can be found chapter 2 of the manual. First of all, strength in numbers. So this approach is going to look at the effect of high densities of structures, but we're not putting a lot of effort into designing those structures, and they have a temporary sort of status to them, and that defers some of the, or a fair amount of the decision as to how they're rearranged to the river and to how the river utilizes those structures to create new habitats. As Nick mentioned, Asotin is like Bridge Creek. It is an intensively monitored watershed, and these two locations are shown on the map here. Asotin being in southeast Washington. The primary goal of the Asotin IMW is to test the effectiveness of low-tech, large woody debris additions at improving freshwater rearing habitat for steelhead, and ultimately the effectiveness of them at increasing steelhead production. The project began in 2008. It's ongoing. It's in southeast Washington, and it focuses on 3 tributaries in the mid to upper part of the Asotin watershed, all on state land. We have a detailed experimental design referred to as a staircase design, which staggers the restoration treatments over multiple years. We've done some simulation modeling to show that this design is actually more powerful than a traditional Bocce design, and it also has the advantage of being easier, more logistically feasible to implement. So we divided each stream into 3 sections, and each section is about 4 kilometers long. And we have habitat and fish sampling sites in every section. And we treated 1 section in each stream starting in 2012 through 2014, and then we added an additional 2-kilometer treatment to the South Fork in 2016 to have a total of 14 kilometers of treatment in a 36-kilometer study area. Just summarizes a little bit about the streams and the setting. We have very dry climate, probably less than 10 inches of rain in the lower part of the watershed. But all 3 streams are flowing from the Blue Mountains, and so it's high enough that they have snow-dominated flow hydrology. And each stream is a little different in its gradient and discharge, and so we have a nice experiment where we have different types of streams that we can attest the effectiveness of this approach on. The riparian areas are dominated by 20 to 40-year-old alder that appear to be locking the stream in place, and this results in predominantly planar geomorphology, or what we refer to as bowling alleys. They're fairly devoid of woody debris. And these streams are very efficient at moving sediment and wood out of the system. Here's just a shot from a drone of Charlie Creek, showing that it's also, these streams are predominantly disconnected from much of their floodplain and only have a narrow riparian extent. So now I'll talk about what we proposed to do to treat this. So we developed the post-assisted log structure approach in Asotin Creek to deal with a wood deficit, structural starvation, and PALS or post-assisted log structures are hand-built structures that use wooden fence posts to pin small pieces of large woody debris in place with the goal of mimicking, promoting, and sustaining wood accumulation. When we build large numbers of PALs, we call that high density large woody debris treatment. And the goal of this is to build a large extent of structures at high density and low cost, and also low impact, so that we're not impacting the existing riparian. Here's just some pictures of the different types of PALs that we've used. Bank attached, mid-channel, and channel spanning structures. And these are all detailed in the pocket guide and the chapter 4 of the manual. And here's some cartoons of those structures, and we'll talk more about the construction of those in Module 5. We have a extensive restoration plan for Asotin Creek, and one of the things that we did was develop a series of hydraulic and geomorphic hypotheses about each of the structure types as to what kind of responses we'd get from the structures. That's sort of depicted in this cartoon with the different hydraulic and geomorphic potential responses. And then we set about testing these responses in the IMW. If you remember from Nick's talk, we have intensive monitoring of both habitat responses and fish responses. And just like Nick's Bridge Creek talk, we then took those hypothesized hydraulic and geomorphic responses and linked them to potential fish responses, and then set about to test as many of those fish responses as we could. So the overall treatment ended up being 700 PALs, between 130 and 200 PALs in each stream, treating a total of 14 kilometers out of the 36 kilometers of the study area, or about 40% of the study area, at an average cost of between $30,000 and $50,000 a mile. And this figure just shows the sort of density of the structures. It turned out to be about a structure every 20 to 50 meters. All right, so what did we find first with the physical responses? Well, indeed, the PALs did diversify the hydraulics, which led to many geomorphic changes, including increases in pools and bars. And the bars creation was particularly striking because of the dominant planar structure before restoration. As soon as we put wood in the stream, we just started to see bar formation everywhere in and around the structures. And it became apparent to me in particular as a fisheries biologist how important the development of bars are, as they are going to be one of the predominant processes that help to force overbank flow and eventually floodplain connection. This graph just shows one single PAL donated by the brown line in the middle of the figure, and then each panel is different year, starting with pre-restoration on the left and moving to post-restoration on the right. And each of the colored squares represent a type of geomorphic unit defined in the upper right. And the takeaway messages here is when we started and built this structure in 2012, it was very simple, had mostly run and rapid habitat. And within a few years, we have multiple geomorphic units showing up, including bars and pools. And if we take all of the structures, and in this case, it's looking at over 100 structures in the South Fork treatment, one of the treatment areas. Each bar here shows a different year, and the bars represent the proportion of geomorphic units, and it's split by pools, bars, and planar. And the top panel is what's happening above the structure, and the bottom panel is what's happening below the structure. And in both cases, you can see there's this general trend toward increasing pools and increasing bars over time, and a decrease in planar features. And that is probably larger effect downstream of the structure than upstream, but both are pretty striking. And so that's sort of a summary, a real brief summary of just what we're seeing in the channel. We're seeing this increase in channel complexity, but we're also starting to see this connection to the floodplain and relic side channels, including the creation of backwater habitat, which are important for juvenile fish. However, these are fairly small changes because of the time it takes to start to force this floodplain connection using PALs. It takes time to build up the bed and to start to increase aggradation. So I'd estimate right now we're at like 5 to 10%, maybe a little bit more increase in the active floodplain from when we started. However, when we had a big flood in 2017, we saw maybe a little bit more floodplain connection. This is just an aerial shot of that. You can see the structures in the channel forcing overbank flow. Another thing we're seeing, and that we had hypothesized, is that we would see some structures move and wood being lost off of some structures, but because of the high density of PALs that we built, that we would see that wood accumulate somewhere else. And this is just a picture showing a large debris jam that built up on one of our structures, and a lot of that wood came from other structures that were upstream. This graph just summarizes this for all three streams, so each color represents a different stream, and then it's the percent that are either completely gone on the left or completely intact or larger or even new structures on the right. And the two red arrows there are just drawing your attention to the fact that we, on average, lost about 10 to 15% of the structures are completely gone, but that was more than made up for by the structures that got larger and the new structures that formed from this wood that we had added, plus natural wood as well. And so now we have about 750 structures when we started with less than 700. Another exciting thing we're seeing is the recruitment of trees. And so we actually used bank attached PALs to try to recruit trees in places where they were already starting to lean into the stream. And so this is sort of an indication of the beginning of sustainable process of wood recruitment and wood accumulation. All right, what happened to the fish? Well, this graph shows the percent change on the Y and the three streams on the x-axis. And the black dots represent the estimated change in fish abundance in the treatment sites relative to the control sites, and the bars are the 90% confident intervals. And so what this shows is there was a positive change in all three streams in abundance, with 2 out of the 3 streams being a significant change. And these percent changes in abundance are approximately equivalent to about a 15 to 40+% increase in fish abundance across the study area. And that translates to between 130 and almost 800 fish per kilometer more in treatment areas now than in control areas. What's really interesting is that if you contrast these changes with between the Asotin IMW and Bridge, what you see is that we've got this great increase in channel complexity, but a minor increase in the overall extent of floodplain connection. So only maybe 5, 10, 15% increase in floodplain connection, which translates to this 12 to 42% increase in fish in the Asotin, whereas in Bridge Creek you have almost 230% increase in floodplain, active floodplain, and that has a much bigger increase, results in a much bigger increase in fish abundance. So the takeaway here is, more habitat, more water equals more fish. And so our goal now is to try and connect more to the floodplain in the Asotin and see if we get this same increase in fish abundance. All right, and just to wrap up with the status of the Asotin IMW, this picture shows the location of a structure that used to be there and is no longer there. And we have our whole restoration plan is developed around an adaptive management framework. And we hypothesized that some structures would move, and sure enough, some did. And until the natural recruitment of wood keeps pace with this movement, we need to feed the river more meals of large woody debris. And so we're now in a phase where we're doing maintenance or enhancement and adding wood, and we're able to do that now in a much more, even more cost-effective way. Because of all the alder that are around, we can just fall alders on some of the structures, or even just add wood, what we call seeding, and that gets caught on other structures. And so we're now feeding wood and also trying to build some structures up so that we can force more overbank flow and see if we can get more active floodplain, and if that gives us this greater increase in fish abundance like was seen in Bridge Creek. So just to sum up, we're finding that this high density large woody debris approach based on high densities of PALs is practical, cost effective, and appears to be scalable. We're getting great increases in geomorphic diversity within the channel, and we're slowly pushing the system to reconnect to its floodplain, and continuing to do maintenance on the treatments to accomplish that. And we're seeing some moderate but pretty significant benefits to fish, with more analysis to come on from us continuing to do maintenance. And with that, thank you very much.